Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Advantest with Ira Leventhal, who's going to talk today about using AI to improve the dependability of chips. Ira, AI seems to be everywhere these days. It's being used for a lot of different things. It's showing up in chips. It's being used to actually improve the chips. It's being used in systems that we never thought it would be used in. But one of the issues is we have to improve the reliability, the dependability of what's coming out of these AI chips. So what are you seeing in terms of how is this being accepted by the market? What has to be done to move it forward?
Well, obviously, there's been a tremendous amount of hype about AI in many different ways. AI has been around for 70 years now, and it's gone through several cycles where there's been quite a lot of hype about what we could do with it, and then that was followed by some disappointment. But it's gone through a pretty good run now, let's say the past 20 years or so, based on the improved hardware, our improved ability to store and retrieve the data and the amount of data that we've collected, and the improved algorithms. So this has really given us the springboard to be able to apply AI in many different ways. And one of the things that we're focusing on at Advantest is what are the right ways to apply AI such that we end up with chips that are more reliable, more dependable, and when we put them in systems that we need to be dependable, such as self-driving cars, medical devices, and so on, that those systems in turn are as dependable as possible.
So what has your research shown?
Well, we've looked at a variety of different ways that we could apply AI, and my colleague Jochen Rivar and I have been focused on this concept of what we call explaining AI. You hear a lot about trying to get to explainable AI these days, and the idea of explainable AI is things like the deep learning models are typically black boxes where they make very complex decisions, and we don't typically know exactly why they made those decisions. So if you're going to apply a deep learning model in something where you're looking for increased reliability and increased dependability, you need to apply that very carefully. When we look at it, we think more about the concept of explaining AI. The idea being that we can, whether it's deep learning models or other types of machine learning algorithms, we can use those in ways that help give you greater insight into what's going on with your chips and make them, in the end, more reliable and dependable.
Why don't you draw this out for us?
Sounds good.
So what are we looking at, Ira?
Well, so let's talk about what's happened in the past 70 years with AI. What I've plotted out here is kind of the popularity, the amount of funding and so on that has gone into AI over that time and what we've been able to do with it. So starting from 1950, that's where Alan Turing first came out with the concept of being able to develop a computing machine that mimicked a child's brain, then have that machine be able to train itself and from there develop into something that could operate like the adult brain. So a lot has happened in the 70 years since then. And AI has gone through these periods of where there's been a lot of hype and a lot of funding into these areas that we call the AI winters. And what's typically happened is there's been a lot of excitement followed by disappointment because the ideas were really ahead of what the technology was able to deliver on. In the case of the first AI winter, you had many great ideas that there was nothing near the computing power to be able to deliver on. So there were some nice demos, some nice prototypes created, but the funding dried out because you just weren't able to do a lot of real-world things with it. And that came in the mid-1970s. You had through the 80s, you had that first AI winter. Then things took off again with the idea of expert systems. People became really enamored with the idea that these systems would be able to make decisions like humans. And to solve the problem of the lack of computing power, specialized AI systems computers were developed to support the expert system algorithms. But what happened was these specialized systems were not only too expensive, they were difficult to maintain, and the algorithms were not even that good. So now in this mid-80s through mid-90s, you went through this period of the second AI winter where the funding was dried up based on the disappointment. So what we've been looking at is what is something that could trigger the next AI winter? Since that mid-90s period, we've been through a period of explosive growth in AI. And now you see the big hype is around things like autonomous vehicles, medical devices. And these are really mission-critical types of applications. So the important thing with these applications is those systems need to be dependable. And if we're using AI in those systems and it fails to deliver on the dependability requirements, that could lead to the next period of disillusionment.
What determines a chip that's dependable versus one that isn't? Is it a matter of just the standard testing that we've been doing in the past, or is there more to it?
Well, the failure mechanisms of the devices are becoming more complex. So we've used various means for determining passing versus failing devices for a number of years. But it's becoming more difficult to apply those same techniques and achieve the same level of quality and reliability.
So this is not as clear-cut as it is for just a standard chip, right? Because these chips learn, they react differently as they go into the market, into actual use. How do you make sure that what you're testing is the right thing?
So this is very important, especially as you're looking at chips that are going to be used in mission-critical applications like self-driving cars or medical devices and so on. And so looking here at what typically we're trying to achieve when we're testing a device is you have your good and your bad devices, and your testing is supposed to separate those two out. And so you want to pass the good devices, you want to fail the bad devices. But the testing is not perfect, and as I mentioned, the failure mechanisms of the devices are getting more complex as we go to things like new process nodes, more complex designs, and so on. So what we're looking at is what are the various ways in which we can apply artificial intelligence-based algorithms to help us out in this testing process. And a very important question is, what are you looking to achieve? Because there's two things that can go wrong when you're testing a device. One is that you can fail good devices, which is going to cause increased yield loss. The other one is you can pass bad devices, which is what we refer to as test escapes. Now, if you look at the consequences of each of these, the thing that you really want to avoid is these test escapes. So there are things we can do with AI algorithms that can help us make pass-fail decisions with a greater level of complexity and weed out some devices which normal pass-fail algorithms wouldn't catch.
What you're doing here, though, is you're using AI to test AI chips, right?
Absolutely. This is something that AI chips are absolutely becoming more prominent. Amazon just announced a couple weeks back that they're releasing their server-based AI chip. And so testing those chips is becoming a great area of interest as well as concern for the industry.
And there's this whole new area called the edge, which has never been fully defined. That's going to have a lot of AI in it as well, a lot of AI chips. Again, this same technique applies of using AI within the manufacturing in order to improve the dependability and reliability of those chips.
Yes, the key thing with an edge computing application being effective is it's going to have to make the right decisions out on the edge, and it will typically have some, let's say, lower powered capability in your edge computer that is focused on making some sort of AI inference type of decision. So it has to be reliable and dependable.
When do you use it? When don't you use it?
So as far as when to decide to use the AI technology and how to apply it, it really comes back to looking at this chart here. When looking at test escapes, we look at how we can use the AI to avoid test escapes. And so we would look at taking AI techniques and using those to augment our existing ways of determining pass-fail. And then when you look at this category of yield loss, so yield loss, obviously it's something that people want to avoid, but the negative consequence of yield loss, you will lose some money based on your yield loss, but you will be willing to trade off a certain amount of yield loss for being able to once again weed out some devices that would, say some bad devices that you would normally be passing if you don't make the if you don't apply the AI algorithms to the process.
Can you also use the AI to figure out where you apply the test, where you don't, what needs to be tested, what doesn't, and in what order?
Yes, absolutely you can. You need to be careful when you do that, because let's say if you determine that certain tests are not required because something like you have a deep learning algorithm that can make a decision based on a shorter number of tests, you need to make absolutely sure that any tests that you are eliminating are truly not necessary. Because if you end up having the elimination of those tests cost a test escape because you were just trying to save some test time, that's something that if you take that chip and you put that in a system that you need to be dependable, then you're going to face a lot of issues by making that decision. So those techniques have to be applied very carefully.
Another concept that fits in here is supervised versus unsupervised learning for AI. How does that apply here?
So in the semiconductor space, this whole area of supervised versus unsupervised is very interesting in that if you look at the challenge that we face, in semiconductors we have processes that are well established, that are mature, and some of the older, less complex designs are still being run on these older processes. And so we have a lot of data that we've generated on those processes. But also, we're not really pushing things at the leading edge there. So having that data and being able to develop supervised learning models really doesn't buy us a lot because we understand those areas well anyway. But then when you look at the problem of how do we look for defects in the newer process nodes, the more complex designs, there's going to be all kinds of failure modes that we haven't seen before. So by definition, we don't have the supervised learning data to be able to look for those failure modes. So the unsupervised learning techniques come into play, things like whether they're advanced clustering techniques or more complex unsupervised techniques like generative adversarial networks. These techniques can be applied to do things like outlier detection and look for new and different failure modes. So unsupervised learning is something we see as very key as far as how we want to apply AI within the semiconductor industry.
In theory, you should be able to find a lot more defects and problems than you could not using this, right?
Absolutely. With the designs, with the failure mechanisms becoming so complex, it becomes extremely difficult to write some sort of programmatic, kind of if-then-else pass-fail determination for a part. There are all kinds of hidden relationships, very complex and difficult to find failure modes. And of course, if we haven't seen the failure before, it's not something we're going to be looking for. So it becomes extremely difficult to write a program to catch something you've never seen before.
How does this get incorporated into the design for test plan that is developed at the architectural level?
So one of the things that is very important as far as looking at the entire semiconductor manufacturing flow is you do have to go all the way back to the design and look at what's being done in the design process, what's being done in manufacturing, what's being done at all your different test insertions that are leading to provide the kind of quality and dependability that you're looking for. So one of the things that we need to do a much better job of in the semiconductor industry is how we can tie the data that's generated from design all the way through to system level test of the end device, correlate that data to make sure that if we see problems at the end of the process, we can point back all the way to what happened potentially even in the design to create that problem.
One final question here. As you add AI into the testing procedure, does it cut down on the test time and add more reliability into the test itself, or does it potentially add more to what people are already doing?
So I would recommend that the focus, especially in the shorter term, is how we increase the reliability. There are definitely ways that test time can be reduced, but as I mentioned, we need to be very careful about how we apply those and make sure we avoid test escapes. As we have a better understanding of the more complex deep learning models and how we may be able to use those to create more efficient test flows, then we'll have a greater confidence at that point to be able to eliminate certain tests.
Ira Leventhal, thanks for a great explanation.
You're welcome.